All right, this is 8th grade science, 11.4. And orbits and satellites is what it's talking about there. So read it first. All right, so of course we've talked about lots of different types of space flight and that kind of thing. But the really awesome thing is what they can do in space. So obviously they put the Hubble Space Telescope out there in orbit. Then they realized that they can put other types of satellites out there in orbit. And even when we fly out there with ISS or any of those space stations, they have to be able to get into orbit. They don't just, use all their gas to be able to fly around, or fuel, should I say, not gas. So a satellite, remember, is anything that orbits, a planet or something along those lines. So the moon is the natural satellite. These are some other satellites that we're going to talk about in the second part of 11.4. And they allow us to be able to navigate and have cell phones and pictures and military things and all that. So that's really cool. But they base the orbits on the Kepler's laws of motion. So if you remember Kepler's planetary laws of motion, that basically that everything moves in an ellipse, so it's a perfectly shaped oval. The sun is in one of the foci, and just a random point in space is the other foci, which is like the middle 2 points of the oval. And then that's the first law, that everything goes in an ellipse around the sun. Then the second law is as it approaches the sun, it goes faster, and it gets farther away, it goes slower. And remember perihelion, aphelion there. And then the farther out they are, so farther out they are, then the longer they are going to take to get around the sun. So it doesn't take Mercury as long as it does Neptune, obviously. To us, it's common sense. To them, it was not at that point. So anyway, so they use those same laws for orbital laws, basically. And it's kind of an updated version of those laws for rockets. They have to turn the rockets on to get into those certain orbits, and they follow those 3 principles there. And they'll basically, for all of the 3 principles, the spacecraft's initial movement is going to be parallel to the ground, and the ground that's directly beneath it. And then, for example, a spacecraft or a satellite with nearly a circular orbit, so this one might have a circular orbit of the Earth at an altitude of 250 miles, it must be moving at a speed of 17,200 miles per hour. Yeah, that's fast. If a rocket accelerates a satellite to this speed and height, the satellite will move steadily in a circular orbit around the Earth. If the same satellite is traveling at an altitude about 500 miles, then it's going to need to travel about 16,700 miles an hour in order to maintain its circular orbit. So obviously there's a lot of math that goes into it, and they know exactly what speed they need to be going to get into a certain orbit, and they know exactly what the altitude is that they need to be at in order to achieve that orbit as well. So the same idea, like with perihelion and aphelion, is also apogee and perigee, which you'll see on page 363. And apogee is just the highest point in the ecliptic orbit, like an elliptical type orbit there. The highest point would be apogee, and that basically means away from Earth. So it's the farthest point or the highest point away from Earth in the orbit. And perigee would be the lowest point that it could be. So if you're thinking this way, highest point, lowest point, that would be apogee and perigee there. After the satellite whips around the Earth at perigee, it's going to move away from the Earth, losing speed. And then once the satellite reaches apogee, then it sinks towards the Earth again as well. Page 364. Talk about 3 different types of orbit there. geostationary orbit. That's one of the best known orbits there, and that is when a satellite stays above the same point on the Earth's surface, and it basically moves with the Earth's surface. It must be directly above the equator in order to do this at a certain altitude. It has to be a circular orbit, obviously, on that one. And so it's traveling 6,897 miles an hour, which is, of course, faster than the surface below. But if you realize, it's got to travel faster if it's out here, and this is the surface of the Earth, so it's got to travel faster in order to keep up with the Earth's rotation. So that is the geostationary orbit. So sometimes they'll put satellites in that, and you basically can look up in the sky at night and you see a satellite. It's always the same satellite. It's a geostationary orbit. But again, you have to be closer to the equator to be able to do that usually. Or, you could see it still. But anyways, another type of orbit is the polar orbit. And that's going to be around the poles. And it's a satellite in a polar orbit. It travels perpendicular to the equator. And it's going to go from pole to pole there. And so this is, think of this as the axis of the Earth and the North Pole there. And so it's going to be able to go North Pole, South Pole. And that's called a polar orbit. And some satellites do that. And it encircles the whole Earth, though, just so you understand that, not just around the poles. Then you have sun-synchronous orbit. And these are some of them. This is basically where they cross the equator at the same average time as the sun, and it's typically about an altitude of 400 to 450 miles above the Earth's surface, and it can complete an orbit in 1.5 hours. So it just actually passes the sun where the sun is going to be at. It doesn't actually go with the sun there. All right, so they will adjust their orbits depending upon what they need to have done. And so sometimes they use the Hohmann transfer orbit. And this is just sometimes called a transfer orbit. They will adjust their speed, fire their rockets to get into that orbit or something along those lines, and then get to that. And then once they get into that orbit, they kind of shut those rockets off and let the orbit take them there. All having to do, of course, with the gravitational pull, and all of that. It's almost uncomprehendable to minds like me, but these amazing engineers and people, these astrophysicists and stuff, they get it, they understand it, thankfully, and sometimes they'll be able to, those satellites have rockets on them to be able to transfer those orbits and that kind of thing. But these are unmanned satellites that we're getting ready to talk about on page 366 to 369, basically. And I do have a a sheet of paper that has all these on them with notes that I'll probably send you guys. Astronomical satellites, those are the first ones there. And this would be like the Hubble Space Telescope. So it's out there basically with lots of telescopes. It's basically to study the heavens, to study the other planets, to study the Earth from that viewpoint. But mainly it's there to study space, Earth space, not like the other types of, like we have Earth observational satellites. It's not going to study that kind of stuff. It's going to study mostly what's out there in space. And some of them have special telescopes. Some of them will detect radiation. Some of them will study like all of those X-rays, gamma rays, microwaves, all of those things that are out there. And then they'll just study, some of them can detect like distance to the stars, distance to the sun, that kind of thing. Then you have communication satellites, and this helps relay telephone conversations, TV. It helps them to have satellite phones in the military in particular, like in the remote jungles, remote deserts, that kind of thing. TV broadcasts, this will help that. So it also sometimes helps sailors, pilots, that kind of thing. And many communication satellites are geostationary orbits, and they'll stay in the location and then they transmit from one to the other. And then you have weather satellites that basically is used to predict weather, study cloud patterns, study clouds, study all of those kinds of things. They usually take about less than 2 hours to travel around the Earth. And so that's going to really help them to be able to figure out the cloud patterns, because it's like all at once to a certain extent. Then you have navigational satellites, which pretty much all of us have right here in our little phones. And a navigational satellite is constantly transmitting information about its time, about where it's at, about what it's seeing. Radio waves also are used with these satellites. And then, of course, our GPS. Those are all driven by navigational satellites, or ours are little receivers, basically, in our watches and our phones, that kind of thing. Those are navigational satellite receivers. Then you have Earth observation satellites. This can help with crop rotation, crop prediction, forecasting. It can help with spotting forest fires. It can help with surveying cities, fish and bird migration. It might be able to help with that and be able to see that. It might actually even be able to discover coal or oil or those types of valuable minerals and materials. They can perform odd jobs, even like detecting electromagnetic radiation. So these are just really something to help all the scientists be able to study the Earth, study us there. And then you have military satellites. These are usually equipped with missiles. These are equipped with mega photography. Mega cameras to be able to have foreign military configurations, be able to figure all of that out. And during a battle, satellites can monitor movements of enemy ships and that kind of thing. They'll be able to figure out where certain types of people are, be able to see them, be able to send our snipers in if we need to those places. I mean, they're pretty awesome, the military satellites. Then you have unmanned space probes. These are not satellites necessarily like we've just been talking about. They're a little bit different. They actually launch specifically to explore the unknown. So they can go to other planets. They can go, as long as they're equipped to be able to handle those temperatures, they can go to other planets. And the first Earth orbiting satellites were space probes, just to be able, they had scientific instruments on them, and they could help. They had the very first pictures of the far side of the moon, because we've never seen that until then. And they would survey the sun, survey other planets, that kind of thing. We obviously haven't sent one to the sun yet, and we'd have to be able to handle mega temperatures on that little space probe. But we have been able to send them to planets that, and that kind of thing. They can study asteroids or comets or that kind of stuff. So a space probe sent to another planet has to escape Earth gravity. Our gravitational pull is what's allowing them all to stay in orbit. So if it is getting away from our gravity, it has to reach a particular speed, and that speed can escape our gravity depending upon the altitude. The speed is called escape velocity. So it has to be able to escape. It has to reach a certain velocity in order to be able to escape our gravitational pull. 25,000 miles an hour at Earth at Earth's surface is about 25,000 miles an hour, because the spacecrafts are slowed by Earth's atmosphere. So it's got to reach that before it gets out there. It would need to travel if a satellite is about 400 kilometers above the Earth's surface, it would need to travel at 24,300 miles an hour, while a satellite at 239,000 miles above the surface is going to only need to travel 3,200 miles an hour. So it's got to go fast, but then it can slow down. Does that make sense to understand that? If not, look at 368 escape velocity and read those couple paragraphs there just so you understand that, because that's pretty neat. And then, of course, all of those are going to have TV cameras, infrared and ultraviolet sensors, instruments like telescopes, things that can detect magnetic fields, all of those types of things to be able to, they want to discover the unknown, obviously, but they also wanted to be able to discover things that will help us in our life. So, all right, so that's basically, I think that was 2 lessons, basically, 11.4a, 11.4b. Then you can answer section review 11.4, and I will be back with review over chapter 11, and that's pretty much going to be the majority of 8th grade science is just working on that study guide and reviewing over chapter 11, so whenever we do get back together, then you can have all this ready, 11.1 through 11.4. Make sure you have all that. Make sure you have activity 11A and 11B that I gave you done. And then for the next week, that is basically your work, is to do the study guide. So normally that's optional, but this time it's not, since we're not together. And then we'll review over it all when we get back together. And then, but you want to stay, just in case if we happen to have school that week, you'd want to like wait and do it that week. Yeah, so we'll see. Anyway, all right. Stay safe.